Hello everyone, my name is Simon. I'm a chemical engineering sophomore student, and today I'll be presenting my final project that's about using differential equations to model the growth of Earth population. Okay, so before starting my presentation, I would like you all to know that all the data and information that I used to develop this project was taken from this article called Population Growth and the Logistic Equation by Matthew Wilkins, David Austin, and Steven Schlicker. This article is posted in this web page called Mathematics LibreText, and here I leave you the link in case any of you want to check it out. So, growth of Earth population. This is considered to be one of the most pressing issues of our time. We all know that there's a lot of people, well, at least most of all know that there's a lot of people living currently in this planet. There's about 7.9 billion people, so almost 8 billion people currently living on Earth. But have you ever thought about what will happen to population? I mean, will it continue to grow or will the population level off at some point? To answer those questions, we can use differential equation models as the following. The first model we consider says that the rate of change of the population is proportional to the population, and it is represented by this very simple differential equation here. At first, it seems reasonable to interpret population growth this way, because if you have a small amount of people, there will be fewer birth and death, and a smaller rate of change. On the other side, if you have a bigger amount of people, there will be more new people being born and more people dying. So the rate of change will be larger and larger. But there's a problem about this model. If we use it and we keep using it to very far in the future, it will predict increasingly large rates of change, meaning that it will predict that the population will grow in arbitrarily large. If we stop and think about it, that doesn't make sense, because it's a fact that the Earth doesn't have enough resources to support such a large amount of people. So that takes us to our new model, the second model, the logistic equation. What makes us expect that this new model will give us a more realistic result? It is all because of this constant right here, the per capita growth rate. In the previous model, we consider it to be constant. What happened? What does it represent? The K constant is the ratio of the rate of change of the population to the population. So, as I said before, here it is considered to be constant, constant, constant. So the ratio will always be the same. So if the population is growing, the rate of change will be growing, and so on, so on, so. But what happens? This is not how it works, because if we think about it, if the population gets larger and larger, there will be less resources to support people. And we assume that the ratio of the rate of change and population will be lower and lower and lower. To consider this, that we use the logistic equation and we'll be able to predict long-term behavior of population growth. Here we have a general form of the logistic equation. As you can see, it's a very simple differential equation that contains two constants. So using this differential equation, we'll be able to answer multiple qualitative questions about the population growth over time. This first constant that we see here is the one that I talked in the previous slide. It is just the per capita growth rate. And here, this is a new constant that we call the carrying capacity of the population. This constant represents the stable population that can be sustained by the environment. Here, you see that there is no specific initial condition, because everyone who evaluates this thing can arbitrarily choose a year to start evaluating the behavior of the population growth. For this project, I chose the year 2000 to be the T0. And according to tables given in this previously cited article, we know that the population in this year was of 6.084 billion people. Also, these two values for this constant were also taken from the tables and calculations in the article. Following, I show you the Simulink block diagram that I built to evaluate this differential equation. It is very simple because we're working with a singular differential equation, and well, describing it quickly, this block here represents the n, the n constant, and this block here represents the k constant, and all the other blocks are just the blocks that make the respective computations to get a result from this equation. We click here with the scope, and we see that the differential equation used give us a exponential curve with a horizontal asymptote in 12.5, around 12.5 billion. So it is important to know that here in this y-axis, all these numbers or in the scale is in terms of a billion. So here it represents 6 billion. And as we said before, in the t0 times 0 is represented by the year 2000. And here the population was of 6.084 billion people. And here in the x-axis, this year are years after the year 2000. So here will be the year 2050, the year 2100, and so on, so on, so. From this graph, we can interpret a few things. First, we see that the population starts to level, the population level off at 12.5 billion, which is that fairly agrees with the carrying capacity, which makes sense because that's the stable amount of people that the environment, being the earth, can sustain. See here that in a few years, the population will keep to grow and grow and grow very quickly. But then when we get to the year 2150 and longer, like after it, the rate of change of the population will be very, very, very small and will be very close to the number we just said, 12.5 billion people. So moving to that conclusion, if we assume that the rate of growth is proportional to the population, we're led to a model in which the population grows without bounds. However, if the per capita growth rate is assumed to be decreasing, as it is in this case, we're led to the logistic model of population, which predicts that the population will eventually stabilize at the carrying capacity that's around 12.5 billion people. Using the scope that we saw before, this one, we can predict what the population will be in any desired year. So, for example, if we want to know how many people is expected to be in the year 2150, we can just go here and look at this number. It will be around 12 point something, maybe 12.2 billion people. And we can do that with any time. And to finish, I would like to let you all know that the logistic equation can also be used for modeling any situation in which limited growth is possible, such as the following. You can model the spread of a virus in a limited population. You can model the spread of rumors in a small town, or even the behavior of animal population on an island. So, well, that was it. I hope you all enjoyed my presentation. Thank you for listening, and I hope you all have a very good end of your semester. Bye. Thank you.